Alright, so the sixth question is the lifetime of an electronic state would be the following. So they have provided the lifetime of various steps like fluorescence, thermal de-excitation, intersystem crossing, photo bleaching, quenching, etc. So they have actually mentioned the lifetime of this process. In reality, all of these happen together. What are the observed lifetime and the fluorescence quantum efficiency respectively? So let's understand the basics of this question first, then we'll definitely solve the question. So we have been given with the lifetime of different process, but in reality all of these happen together. So what they want to say from the statement is, let's say let's take an example of fluorescence because we have to figure out for fluorescence itself. So what is fluorescence? Fluorescence is actually let's understand the kinetics is of fluorescence. So what is fluorescence? Fluorescence is actually when S star, right, if we have an electron in excited singlet state, it basically come back to your ground state with radiation. So it's a radiative process. Fluorescence and phosphorescence, they are radiative process, right? So they have provided the various steps in which fluorescence is happening. But with the fluorescence, there are number of steps that happen simultaneously. Okay, so let's write down each and every step. So first is if only fluorescence occurred. So if like first step is we have one step in which fluorescence occurred. Okay, so that is S star come back to S naught plus H nu. This is the first step. Okay, second step is if only thermal de-excitation occurred. So what is thermal de-excitation? That means excited state particle comes to the ground state, right? Thermal de-excitation. So basically it has absorbed some energy, it went to the excited state, then it just came back to that ground state. That is thermal de-excitation. Okay, basically it's a process of de-excitation. Third step is if only intersystem crossing occurred. Okay, what is intersystem crossing? Intersystem crossing is basically when S star goes to T star. Am I correct on this point? Right? Singlet goes to triplet. This is intersystem crossing, ISC. Next is photo bleaching occurred. Okay, so let's say we have one more step, photo bleaching. Okay, so we can say that this is the step of photo bleaching. Right? So what is basically photo bleaching? Let's say at that point of time we are not aware with the process, but it's somehow related to uh, the change of singlet to triplet only. The mechanism is still not known, but we can say photo bleaching is a process. So this step denotes your photo bleaching. Okay, this step actually tells you about the photo bleaching step. All right, next is if only quenching occurred. So what is basically quenching? Okay, quenching is shortening of lifetime of the excited state. Let's say for so and so time, the particle, the electron remains at excited state. If we have to decrease that lifetime, if we have to shorten that lifetime, so we basically add a quencher. So that particular process is known as quenching. Okay, that is decreasing the lifetime of the excited state. Okay, so for that particular step, we can say, let's say we have some excited state. Okay, particle in excited state, we have added the quencher. Okay, what is going to happen? So basically the particle will come to the ground state and quencher will get excited. So that way we have shortened, we have decreased the lifetime of the excited state by adding the quencher. Okay, so this process is actually quenching. That is decrease of the lifetime of excited state. Okay, it decreases the quantum yield as well. That's a different story, but this is known as a quenching process. So we have these process, and they basically asked us to figure out the observed lifetime and fluorescence quantum efficiency if all of these steps happen together. So what I want to say is I'm just giving you a view that how we can actually get to the given formula in order to solve this question. Okay, let's say for fluorescence the rate constant is kf. For like this is thermal de-excitation, so let's write down for kt. Okay, This is actually ISC, so let's write down it for ISC. This is photo bleaching process, so KP. This is quenching, so KQ. Okay, so we have named the rate constant for the given process. Now what we need to do, we need to figure out a formula which relates the lifetime or the quantum efficiency. That is what we need to do. Okay, so all of us are basically aware with the steady state approximation, so I'll be using the same methodology over here to figure out the correct formula. Okay, so if I want to write down the rate, right, if I want to write down the rate as I'm finding it for the fluorescence process, in the question itself they have asked for the fluorescence process, I'll be using that step in order to figure out the rate. So what I can say, rate is actually Kf, right, into concentration of S star. Clear? Now if S star is intermediate over here, or I need to figure out steady state approximation, I'll be doing steady state approximation to S star because I need to figure out the value of it. Okay, right, am I clear on this point? This is what we need to do. So for the very first process, what we need to do, we actually need to figure out the steady state approximation, right? But before this process occurs, what we can say, that the particle will go from the ground state. Okay, the particle will go from the ground state, and how it will go from the ground state, when it will absorb some energy, then only it will move to the excited state, right? It will absorb some energy at the ground state and it will move to the excited state, right? This is the absorption. That is why, in fluorescence step, the particle comes back with the emission of a radiation. It's a radiative process, so definitely it has absorbed some process and then it begin giving back the radiation process. All right, so this is going to be the first step for sure, the absorption. Okay, photochemical laws, right? So this is going to be the first step. So what I can say, if this is the first step, all I need to do is find out the steady state approximation on S star. So S star is present over here. First step is always I absorption. Clear? All right. Next is I can say minus KF S star. Great. Okay, minus KT S star. I hope you all are clear with the steady state approximation. Okay, then minus KISC S star. Clear? Okay, that's how we can actually give this process. Now let's say what is photo bleaching actually. The exact mechanism is still not known, but we can say it is like just similar to the transition from the excited singlet state to excited triplet state. That's another process of photo bleaching. So we can say actually excited singlet state is going to excited triplet state. Okay, so we can say that S star would be present over here as well. So minus Kp S star minus Kq S star and quencher, right? That's how we can write it, is equals to 0. So what is going to be the concentration of S star? The concentration would be IB divided by Kf plus Kt plus KISC plus Kp and plus Kq into concentration of quencher. That's how we can find out the concentration of S star. Then we can substitute this concentration in rate. Basically rate becomes KFIAB divided by KF plus KT plus KISC plus KP plus KQQ. Alright, that's how we can find out the rate. Alright, next is we need to figure out the quantum efficiency. What is quantum efficiency, everyone? So one formula for quantum efficiency is rate by intensity, right? Rate by intensity, we can say. What is rate? We just found out this is rate. If we divide it by intensity, what is the intensity? IAB. So rate would be KF and then this denominator part. Alright. These are the various steps that need to be followed in order to figure out the formula through which we can solve the question. Okay. So this becomes your quantum efficiency. Okay. So If I just bifurcate this particular formula, so basically quantum efficiencies, can I write kf into 1 by kf plus kt plus kisc plus kp plus kqq, right? And what we say that this whole part is actually tf. What is tf? Time period of fluorescence, or we can say lifetime of fluorescence, right? Average lifetime of fluorescence. So the quantum efficiency of fluorescence becomes kf, that is the fluorescence rate constant, into your time period, okay, of fluorescence. This is your quantum efficiency of fluorescence. Okay, that's how we can find it for phosphorescence as well, but over here this is your quantum efficiency of fluorescence. All right, so that's how we can actually get to the formula of quantum efficiency of fluorescence, which is qf, right? This is the formula. All right then, next is we need to figure out the observed lifetime, that is tf, and we need to figure out theta f, that is your quantum efficiency. That is what we need to figure out. Now let's look at this particular question, and let's try and find out the given question. Now we know, see, okay, let me tell you one important thing. Can I say this thing that t average or the lifetime is actually equals to 1 by k, that is your rate constant? How we can say that? For example, what is rate? Rate is actually concentration by time, right? Rate is actually concentration by time. If we need to figure out average rate, we can say average rate is equals to average concentration by average time. And we need to figure out average time only, that is, the lifetime or the time period of the given system. So average time becomes average concentration by average rate. Okay, at a given point of time, we can say average concentration of any reactant, let's say A to B, okay, is A, and average rate would be Ka, right? Fluorescence, phosphorescence, radiative process, these all are first order reaction, so order is going to be 1, right? So A and A concentration would be cancelled out, so we can see average time is actually 1 by k, that is reciprocal of the rate constant. Okay, so lifetime or average k for first order reaction is defined as 1 by k. This is only applicable for first order reaction. So average time or time period or lifetime is defined by 1 by k. Okay, so we are going to use these two formulas only. First is this formula, and second is average lifetime is actually defined by 1 by k, and that is how we can derive these two formulas. Okay, I hope the point is clear to all of you. Now we just need to use these two formulas in order to solve the question. So first we would be solving the observed lifetime for fluorescence. Okay, so what is observed lifetime? We can see we have derived this particular thing over here. This is the given formula for the lifetime, right? What we need to do, all we need to do is take reciprocal of the rate constant of these given steps. Okay, so what we have actually 1 divided by fluorescence plus thermal de-excitation plus intersystem crossing plus photo bleaching plus quenching. Okay, so this is going to be the lifetime, and how we get this particular formula. Now all of you must be clear that these are the steps in order to define or in order to derive the particular formula. Okay, and what is k? We know through this formula that k is actually, it's nothing, it's just the reciprocal of the given time or the lifetime. Okay, so we have lifetime of these various process. Okay, so what we need to do, 1 divided by what is kf? If fluorescence lifetime is 5 nanosecond, so rate constant would be 1 by 5 using this formula, yes or no, right? Okay, for thermal de-excitation it would be 1 by 10, For intersystem crossing it would be 1 by 10. For photo bleaching it would be 1 by 5. For quenching it would be 1 by 5. Okay, so let's solve this thing. Okay, so this would be 1 divided by 8 by 10, right? And this would be 10 by 8. So approximately this would give you 1.2 nanoseconds. Okay, so the lifetime, observed lifetime for the fluorescence in which these all steps happen together is 1.2 nanoseconds. And second is you need to figure out the quantum efficiency. Now we have this formula. Quantum efficiency is actually kf into tf, and tf is like 1.25 seconds. We just found out this value, 1.25 nanoseconds. And what is kf? Kf is the reciprocal of the lifetime of the fluorescence process, because we are finding out the quantum efficiency of fluorescence. So over here we have to take the rate constant for fluorescence only. That is going to be 1 by 5. So 1.25 divided by 1 by 5, that would give you 0.25. Okay, because this is also nanometers, so it's going to give you a dimensionless quantity, that is quantum efficiency, 0.25 nanometers. I hope this question is clear. Why I did all these steps in order to give you an idea that this is how we can actually get to the correct definition or the correct derivation. Okay, this is not the required derivation for the question, but that's how we get to this particular formula. Okay, these are the various steps of fluorescence. In the question they have asked lifetime of fluorescence, so we can actually get the reciprocal of fluorescence lifetime. Okay, because in fluorescence all of these steps are happening together, so we have to take the summation of their rate constant and then take reciprocal of it. That's how we're going to find out the fluorescence lifetime and then fluorescence quantum efficiency with this formula. And we got this formula by doing these various steps. Okay, I hope this is clear. Let me know in the comment section if you have any doubt in the question. It's a very nice question, but if you're clear with the photochemical concepts and the photochemical derivation of fluorescence, phosphorescence, quencher, and all of this stuff, this is a very easy question to solve. Okay, all right, I'll see you in the next video.